Okay, so here we have the next question of the day, and it is asking us, or is presenting a situation where we have a long insulating massless rod of length L, pivoted at its center, balanced with a weight W at distance X from the left. Okay, so this diagram is not particularly clear, so I'll redraw this ASAP fast. So let's say that this is our balance point of our situation. And here is our massless rod. On either end of it, we have positive Q on the left side. We have positive 2 Qs on the right side. Okay, and here we have capital Q, which is positive, and here we have capital Q, which is also positive, and the distance between them is H. This length here, the length of this whole unit, is L, and X distance away from the whole left side passes the center point is a weight. Okay, now the weight is not given and the charges are not given, and neither are the distances. Okay, so we're going to be pretty much entirely in the realm of algebra as we solve this question. Okay, but this is the situation here, and that's the pivot point. Okay, so part A of the question is asking us, find the distance X for the position of the weight when the rod is balanced. Okay, so when the rod is balanced, that means that the net forces are going to be 0 in the vertical direction, and as well as the moment about the center is going to be 0 as well when this is all in equilibrium. Okay, so to represent that, let's say we want to find the moment at center. To do that, we want to do something like this. So if we say that counterclockwise is our positive direction, as is a typical convention, at least here in North America, so the moment about C for the center is going to be 0. Okay, so who's thinking about here? We know that these two Q's, they're both positive, and they're going to try to repulse each other. So let's draw in our force here. So Fe for electric force, FEL for the left electric force, and here we're going to have FER for the right electric force. And here, let's just call that our weight force, and those are the only forces, the main forces of interest here. And of course, we're also going to have like a normal force at the pivot here. So let's just draw that in to be 1000% complete. But here, this is going to be point C for center. Okay, so taking a look at the left force here, let's see how this is going to have a moment. It is going in if this force was to like try to cause us to rotate, it would cause us to rotate in the clockwise direction. That's going to be a negative term. So that's going to be negative FEL, and it's going to multiply by the distance that it is away from the center. So that is 1/2 of L. L over 2. Okay, now we're going to look at the weight force. The weight force is also going to try to bring us clockwise, so that's going to be a negative term as well, and it's going to be a different distance away. It's going to be X minus 1/2 of L, because that's the distance from center that it's going to be. Okay, so this is going to be a negative weight force times L over, nope, the other way around, X minus L over 2. Okay, and the last one is FER. This is going to go in the counterclockwise direction. This is going to give us a positive term here, and it's going to be 1/2 L for distance. So this will be positive FER times L over 2. Okay, so this will be our equation here, and we're looking for the distance x. So to isolate for the distance x, we just need to, multiply this all out and do it that way. Okay, so here we're still going to have 0 is equal to FEL times L over 2 minus WX plus L over 2 W plus FER L over 2. Now we're going to try to solve for x, so let's bring that WX term to the other side and divide the whole thing by W. So x is equal to 1 over W times FEL times L over 2 plus L over 2 W plus FER times L over 2. I think that L over 2 could be factored out, but this would be an expression for x. Okay, and yeah, let's actually just factor out the L over 2 for good measure. L over 2W F, the electric force on the left side, plus W plus FER. And yeah, so calculating the forces here is also not particularly difficult. We know that FER is just going to be, or FE in general, just electric forces, is going to be equal to K times Q1, Q2 over R squared. Okay, so finding those, we're just going to like substitute out the F to be in terms of Q's and the R. Okay, nothing too hard with that, but we'll leave it like this just for simplicity's sake. Okay, so that is addressing part A, and that will be X. Part B is asking us, what value should H have so that the rod exerts no vertical force on the bearing when balanced? Okay, so essentially what that means is that the repulsive forces from both of the the charges here, they're going to have an electric force that is like pushing them up. So when is, the upwards push from both of these going to be equal to the weight force? Because that would be the only way that there's no force on the bearing or the, the pivot point itself. Okay, so essentially what that means is we need to make our weight force equal to our left electric force plus our right electric force. Okay, now let's just square this off. This will be part 1. Our left electric force is going to be big Q and little q. So that's going to be K Q over H squared as the distance between the charges, plus K. Now the right side had 2Q, so that's got to be incorporated here. So 2KQ big Q over H squared. We can put these together because they actually are the exact same. So this will just be equal to 3K little q big Q over H squared. And we're trying to solve for H, right? So what we're going to need to do here is just multiply both sides and divide by W. So H is equal to 3K big Q little q over W, all under the root. Okay, so this will be the height necessary for this to have no net force on the bearing itself. Okay, cool. And yeah, that would actually answer the whole question. Okay, so hopefully we came to a similar expression here. So here we have is equal to k q squared over h to the power of 2 times L over 2W. Looks fairly reasonable. And for the other one, we actually this process to do this actually would be better to do this with moments. Okay, cool. So yeah, awesome. Question using moments, or finding the moment about the center of the bar.